I would like to welcome everyone to today's first LiveTalk event for this spring semester 2021 by the Eurostruct Association, which is an association or a network for life cycle assessment of bridges and infrastructure. Maybe by way of introduction, the Eurostruct Association formed as a result of Cost Action TU 1406 on quality specifications for road bridges and standardization at the European level. You can find more information on our webpage, where you will also find more information on upcoming events such as this one. Before we begin, I would like to acknowledge the support of the University of Milano, together with Boutique Studios and the International Federation for Structural Concrete Feed, who are supporting these LiveTalk webinar series. And I would like to also give a few information to the participants. The LiveTalk will be recorded and made available on our YouTube channel. It's the same for all of our. And should keep cameras turned off and microphone muted. And for the Q&A, please send your questions to the Eurostruct Association participant through the chat, and these will be transferred to us at the end of the session for asking the speaker. Today, I'm pleased to introduce, first of all, my co-moderator for the event, which is Maria Pina Limongelli from the Politecnico Milano. And she will be assisting me in co-moderation, but also will present the speaker. So I give her the floor.
Thank you, Eleni. It's my pleasure to present my colleague at Politecnico di Milano, Professor Fabio Biondini. He is Professor of Structural Engineering and Chair of the Civil Engineering degree program at Polimi. Fabio is also founding director of the postgraduate Master in Engineering and Integrated Management of Highway Networks, which is a joint master between Politecnico di Milano and the Politecnico di Torino. Professor Biondini is very active in the field of life cycle risk and resilience management of deteriorating structure and infrastructure systems, with the specific and particular focus on bridges and bridge networks. And he has published more than 300 papers on these topics. Fabio is also co-founder of the International Association of Life Cycle Engineering, and serves with leadership roles in several scientific and technical, scientific association and technical committees. And for his scientific activity, he has also received several honors and awards from academic institutions and professional associations. And now it's my pleasure to leave the floor to Fabio Biondini. Please, Fabio.
Thank you, Maria Pina. Hello, everyone. And first of all, I would like to thank you, Eleni and Maria Pina, for the introduction and the kind invitation to deliver this presentation as part of the Eurostruct LiveTalk series. I'm going to talk about life cycle of bridges and infrastructure networks. And as we know, this subject is of high relevance and topicality in our society. And I would like to inform about some research activities and projects ongoing into this field at Politecnico di Milano and beyond. As we know, in recent years, many studies and news raised alarms about the detrimental impact of aging, fatigue, and deterioration processes on civil structural infrastructure systems, and this is particularly for bridges and transportation infrastructure networks. Now, the effects of this phenomena can lead over time to unsatisfactory structural performance and may have a significant impact on the structural safety, particularly on concrete bridges, I would say. Now, in the last century, engineers have been under the impression that the structure will last for a very long time, as it was observed for old structures such as old masonry Roman bridges and several other iconic concrete structures such as the Pantheon in Rome, for example. Here in this picture, you see the Pont du Gard, and the Pont du Gard and the Pantheon were built about 2,000 years ago. However, the exploitment, the optimization of materials working at high stress levels, the continuously increasing traffic demand, and also the severe exposure to aggressive environments lead over time to serious deterioration problems such as corrosion and fatigue. And this is for most of bridges that were built in the 50s, 60s, and 70s. Now, these aspects are also emphasized by and are made more evident by dramatic events and bridge collapses that have occurred with alarming frequencies in several countries, and these include Italy. Some of these collapses are due to reasons still under investigation, but of course, aging and deterioration played a role. This is also exacerbated by the changing climate, since the modification of environmental condition may accelerate the deterioration rate and also increase the occurrence of extreme events over the structural lifetime. The scale of repair or replacement needs is particularly large and represent a key obstacle for sustainable development of countries. According to the recently released report card for America's infrastructure that is issued by the American Society of Civil Engineers, more than 40% of the over 600,000 bridges across the United States are at least 50 years old, and over 46,000 of the nation's bridges are considered structurally deficient, with almost 180 million trips across these deficient bridges every day. In addition, the most recent estimate puts the nation's backlog of bridge rehabilitation needs at 125 billion. That is a huge amount. The substantial underinvestment in infrastructure repair and maintenance is clearly becoming a major problem in most developed countries. And as mentioned, this includes, of course, Italy, because huge stocks of bridges and infrastructure facilities that were built over the past 50 years are rapidly approaching the end of the service life. In addition, the design of individual structure in the past did not consider the direct monetary losses associated with maintenance and repair interventions, and also did not consider indirect economic consequences at infrastructure level induced by network downtime in consequence of, for example, partial or fully closure of a bridge into the network. To face this need, civil engineering is undergoing a profound transition toward a life cycle-oriented design philosophy, where the classical point-in-time design criteria are revised and extended to account for more comprehensive time-variant performance indicators over the entire service life, taking into account the effects of maintenance and repair under uncertainty. When we are talking about uncertainties, we refer to uncertainties affecting the initial performance of the structure, but also several other aspects associated with the deterioration process, as for example, the damage initiation time, the deterioration rate, the effect of repair intervention in terms of increase of performance, but also decrease of the deterioration rate. And all these uncertainties will accumulate over time and will affect the estimation of the remaining lifetime for the system. Now, in this context, significant advances have been accomplished over the years, and these accomplishments are perceived to be at the heart of a new approach to bridge and structural engineering, where time is the new variable and infrastructure is the new scale. This approach will be of crucial importance in order to consolidate and enhance criteria, methods, and procedures for improving safety, durability, and life cycle performance of structural and infrastructure systems. Of course, in order to afford this approach, we need to be able to evaluate the performance profile for individual structure and entire system. And this is quite an hard task because we need to incorporate in our structural analysis method also a proper modeling of the deterioration processes. And as we know, we have a wide spectrum of damage processes that may affect our structural systems. And Just to make an example here, we are talking about the effect of corrosion on reinforced concrete structures, and we know that these effects are multiple and involve not only steel mass loss, that is the main effect of corrosion, but we may have a reduction of steel ductility that is also very, very important, because this may lead to brittle failure, and also the associated deterioration of concrete that is related to the formation of the oxidation product around a corroding bar, and this lead to have splitting cracks and may lead eventually to concrete spalling. All these effects can be now incorporated in structural analysis methods in a very effective way. Here, just an example to recall the three effects mentioned. So we can take into account of the reduction of steel bar area, take also considering the type of corrosion, for example, uniform corrosion or PT corrosion. We can, based on experimental evidence, build a very reliable model to assess the loss of ductility, that, as it is shown in this diagram, it is a very important aspect, because, for example, for a 10% of steel mass loss, we may have a loss of ductility also of about 50–60%. And also we need to account about deterioration of concrete by reducing the concrete compression strength or the effective resistant area. And in order to incorporate properly this effect, we need also to take into account about the reinforcement layout. This is an aspect that is not important at the initial stage, because very often the reinforcement layout is an aspect that is not driving the design. But when you look at durability problems, this can become an issue. For example, if you have a widely spaced bars, you may have a localized deterioration problem like scaling and border effects, or if you have closely spaced bar, perhaps you can have a complete delamination. All these effects can be incorporated in numerical models. Here is just to make an example, the formulation of a deteriorating reinforced concrete beam finite element that may accommodate all the effects mentioned in order to derive a stiffness matrix that is time variant and allow to perform time variant structural analysis of deteriorating systems. These methods are very well calibrated against experimental evidence, and here you have just a comparison related to some experiments conducted by Rodriguez and co-work at the end of the 90s. And the diagram show the load versus displacement curves associated to this 4-point bending test on simple spacements that were subjected to accelerated corrosion, and different corrosion levels were considered. And here in this diagram, you can see the comparison of numerical versus experimental results for different levels of corrosion. And as you can see, the accuracy of this analysis can be very high. Also, we can capture, which is the development of the deterioration process. On the right-hand side of this slide, you can see a contoured map that show how the damage into the concrete will distribute. And in this case, with only steel bars in the corners, you can see that damage is localized in the corners themselves, and therefore you have border effects. Of course, the case when you have closely spaced bars is different, because you can see also from these other maps how a complete delamination of the concrete cover may occur, and this effect can be easily incorporated into the models that I mentioned, I presented before. Of course, these analyses were conducted for a given level of corrosion, but in life cycle analysis, we need also to take into account about the deterioration rate. And if we refer, for example, to deterioration processes associated to the diffusion of aggressive agents, generally we refer to the fixed second law of diffusion that relate the concentration gradient to the concentration rate by means of the diffusivity of the material. And very often in application, we use the solution of the one-dimensional problem of this differential equation. And this is quite a simplified approach, even though it is very effective, because we have an analytical formulation for the evolution in space and time of the concentration. And this formulation is also incorporated in some design guidelines for service life assessment. In some cases, it is important to consider that 2- and 3D dimensional effects, 2D and 3D gradients of concentration must be considered for accurate evaluation. This equation can be solved in that case with a variety of numerical methods. A numerical approach is necessary in order to deal with complex geometrical and mechanical boundary condition. And among other methods, I would like to mention this approach that was proposed almost 20 years ago for the solution and modeling of deterioration, the solution of the diffusion equation and modeling of deterioration based on cellular automata. And this is a simple approach that refers to a regular uniform grid of cells with a discrete variable in each cell that is associated with the concentration of the component that is diffusing. And the diffusion process can be easily investigated based on this simple evolutionary rule, and the model is calibrated according to a given diffusivity in terms of the grid spacing and time step. And this approach can really provide very accurate results. And if you solve numerically the diffusion equation even for simple problems like the ones that are presented here, you have top left square cross section like you may have in 45 centimeter side, and as you may have in a reinforced concrete building. On the right, you have a hollow core square cross section with side of 2 meters, as is more typical for a bridge pier. And you have in the diagram the evolution of the steel mass loss over a 50-year lifetime for different exposure of the cross section. And you have the comparison of the solution of the one-dimensional analysis with the solution of the two-dimensional process. And you can see that over a 50 years of lifetime, you can significantly overestimate or underestimate, depending on the exposure condition, the amount of damage if you use the one-dimensional solution. Of course, this is depending also on the location of the reinforcing steel bars, and the error is larger for the bars into the corners and less important for the bars that are along the side of the cross-section. This is just to emphasize that there are multiple aspects that need to be considered in order to get accurate results in this kind of analysis. I want to show just an applicative example that refers to this Certosa cable-stayed bridge. This is a cable-stayed bridge in the city of Milan. It was designed by the late Professor Francesco Martinez y Cabrera. And the Milan municipality, after about 15 years of lifetime of this bridge, decided for a detailed inspection of the structure, and the bridge was found in a relatively good condition with some initial damage at the base of the pylons that were the portion of the system most exposed to the traffic emission, and the repair activity, repair intervention was decided, consisting of a replacement of the concrete cover and protection of the external surface with a special mortar that was transpiring outward and waterproofing inward, so to protect the member from the future ingress of aggressive agent. In this concentration maps, you can see the evolution in time of the concentration of the agent, different time instance, 5, 10, 15, up to 50 years, and at the top with no repair, and at the bottom with the repair intervention carried out after 15 years of lifetime. And this concentration maps refer at the cross-section at the base of the pylon. And the comparison clearly showed the effectiveness of the repair intervention that is also quantified in terms of structural performance indicators. And bottom right, you have the evolution in time, for example, of the bending strength of the cross-section. And you can see how is the situation with no repair and after the repair is made. And of course, the repair may increase a little bit the bending strength because we replaced the concrete cover. But this is not the main effect of the repair activity, because the most important aspect is the reduction, the significant reduction of deterioration rate. Of course, this assessment has been made both deterministically and probabilistically. And this is also another relevant issue to be considered, because when you look at the probabilistic results, you can also realize that the effect of the intervention also reduce the impact of the uncertainties over time and make our future prediction more reliable. Of course, this kind of numerical prediction must be also supported by gathering new data, new information based on inspection and monitoring. And these are pictures from a recent inspection that was aimed at checking which was the condition state of the bridge after about 15 years of the repair intervention, and also checking the monitoring system that was installed and used mainly in the early stage after construction of the bridge. And in this period, this system is under evaluation for improvement. In this picture, you can see inclinometers and the load cells, and perhaps additional type of sensor will be considered for improving this system. Of course, the use of cost-effective and reliable monitoring system is of essence for bridge maintenance management systems. However, this monitoring system may be fruitless if not fully integrated, if the results are not fully integrated in a life cycle assessment framework. Here, just to qualitatively show that which are the effects of monitoring that, of course, allow to update our modeling and update the prediction, and this may lead to extend the lifetime prediction, but may also reduce, so that the results of monitoring can allow to improve our evaluation either on the safe side or on the unsafe side. And they may be crucial, above all, to reduce the uncertainties into the prediction. Now, we can, talking about a little bit monitoring systems, we can have systems incorporating traditional sensors, but also innovative techniques. And one of the technique that is most promising, in my opinion, for long-term monitoring aimed at planning, maintenance, and management of bridges is based on the use of geodetic techniques, and in particular of global positioning system or global navigation satellite system, where you have a number of receivers that allow to monitor the position of a number of specified points. Here you can see one of these receivers that is installed on the bridge using proper supports. And when you have a sufficient number of these receivers and properly located over the structure, you can have information about the structural response, the long-term structural response of the bridge, taking out the effect, for example, of the traffic loading and high frequency signals, depending on the time window that is used to elaborate the results. So this is a typical elaboration of this kind of data. You have three displacement time instruments. You have the three displacement components, two in the plane and one for the elevation. The dots, of course, refer to the data that are gained by from the monitoring system and elaborated over a time interval of 24 hours. And in red, you have the interpolation, the modeling of these kind of results. Of course, you can change the time window. And if you, for example, reduce the time window, you can get additional larger set of data. But of course, the noise in this data will also increase, either due to the elaboration of the data themselves, but also because you have here the noise associated to, for example, the effect of the traffic loading. So depending on the time window, you may have a different type of information. And when this time window is sufficiently large, the precision also of this type of measurement may be significant, of the order of 1 millimeter. Of course, you can also accumulate this information over time in order to get cumulated displacements. And this could be particularly helpful over seasonal time window in order to calibrate the monitoring system against also the effect of, for example, temperature and other climatic effects. Of course, when we look at the effect of deterioration processes, we need to account for possible interaction with the effect of natural hazards, such as earthquakes, floods or landslides, and we need additional indicators at the system level in order to account for to evaluate the performance of system networks. And among other indicators, recently resilience is becoming more and more important in the evaluation of infrastructure networks. The concept is briefly resumed into this diagram. If you look at the functionality of the system, if you have an infrastructure network, this could be, for example, associated with the traffic capacity, and you have at a certain point in time an extreme event like an earthquake, the functionality may have a sudden drop, and this drop is the impact of this reduction in functionality is associated to the robustness of the system. However, in order to rapidly recover the original performance and functionality, repair activities must be carried out. And in the diagram, you can see that after a certain idle time, you can progressively recover the original performance and functionality. And the resilience, as you know, is generally associated to the area under the recovery curve over a certain time horizon. This concept is particularly important for regions and countries that are exposed to seismic risk, like Italy, because seismic resilience is an important indicator in order to have a clear information about also the direct economic losses due to repair intervention in consequence of this kind of events, as well as indirect losses due to traffic delay and network downtime. And looking at resilience, taking into account the interaction of seismic environmental hazard, an important point is to emphasize that resilience is a time variant performance indicator. Here you have two functionality diagrams, one for a non-deteriorating system and one for deteriorating system. And in both cases, there are two recovery curves associated to the occurrence of two identical seismic events. Of course, for non-deteriorating system, this will not have any impact on the resilience level. That is the same for the two events. But if you consider the loss of performance in time due to aging and deterioration, also resilience will be affected, and therefore resilience is depending on the time of occurrence of the seismic event. When you face with resilience, we need also to look at one end to the impact of a certain damage and also how to recover this damage. So it is important to establish this kind of evaluation with reference to limit states. In this example in the table, for example, you have 5 limit states. There is no damage, and then in sequence, slight damage, moderate damage, extensive damage, and structural collapse. And for each one of these limit states, for the occurrence and the attainment of each one of these limit states, traffic restriction may be applied, for example, for a road network. You may have, for a slight damage, a weight restriction. You may have one lane open only if you have additional damage, or, for example, emergency access only, or you may decide to close the bridge. And for any action, you have a different loss of functionality at the system level that has to be taken into account and evaluated, for example, based on a traffic analysis in order to compute the traffic delay of people and goods, or perhaps the total travel time between one origin and one destination. And this functionality can be considered for measuring also resilience. In order to improve the resilience, of course, we need to face with this kind of damage and associated limit states with repair activities. However, resilience can be improved not only by ensuring effectiveness of the repair activities, but sometimes you can also design a new architecture of the node network, or you may decide to upgrade the network. This is also very beneficial for resilience, and this is just a very simple academic example where you have this road network with two bridges in sequence along a highway, a detour, and a re-entry link. And at a certain point in time, it is decided to make an improvement, an upgrade of the network with an additional branch and a new bridge. If you look at what is occurring in time, this can be investigated in terms of resilience maps. These maps are referred to different time instances. You have the initial time, 25 years and 50 years at the top without any upgrade of the network, and the resilience map provide a level of resilience depending also on the epicenter location of the seismic event. And as you can see, aging and deterioration can be extremely detrimental for resilience, and you can improve the ability of the system to sustain the effect of seismic events in terms of functionality of the entire system by introducing the additional branch. And you can see the impact of this additional branch in the bottom part of this slide with the new resilience maps that show how this, the effect of aging deterioration can significantly be mitigated by this new branch. However, it is also important noting that it is clear from the last resilience map on the bottom right that after you introduce this new branch, the new branch become a key factor for the effectiveness of the entire system, and therefore it is very important that the bridge B3, for example, is protected against aging and deterioration processes, because this new branch is becoming the most important link into the system. Of course, in addition to resilience, we need to look at other indicators, and clearly when we want to address a bridge prioritization at the network scale, risk is the most important indicator. And here is an example of a recent project that has been established by Politecnico di Milano with Lombardy region. And this project was aimed at the definition of criteria and guidelines for maintenance and management of roadway infrastructures. This project was aimed at developing a risk-based bridge maintenance prioritization methodology at regional scale, as mentioned, and also as a support to the validation and practical application of this prioritization. Structural health monitoring systems were also designed and implemented on a set of 9 bridges, and the overall sample that was analyzed for this risk-based prioritization was of about 400 bridges. The approach was was a standard approach where we have the convolution of the hazard, vulnerability, and exposure, but the peculiarity is the fact that this approach was based on the only available information from existing documents about the bridges, because the main purpose was to provide a support to the bridge authority in allocating the available resources at the local level. And we evaluated the risk at the component level for the hazard and the vulnerability, at the infrastructure level for the exposure. And we defined in both cases priority classes, 4 priority classes that were combined in order to have 4 risk classes. And in this way, we got prioritization of intervention. Here, in a sense, the approach is a risk matrix. You have the bridge reliability on the priority class associated to single bridges on the horizontal axis, the priority classes associated to the infrastructure network in the vertical axis, and the colors refer to the 4 risk levels. And for each risk level, we also addressed the repair strategies that should be underwent in order to mitigate the level of risk for the most exposed bridges. And this will lead to identify and to develop this kind of risk maps that may be used, as mentioned, to allocate the available resources at the local level. Of course, after the resources are allocated, much more in-depth evaluation can be done, inspection procedure, monitoring, and also more detailed risk assessment procedure. This is an example of a life cycle cost-based risk assessment developed for a smaller portion of the network involving 4 major cities and 93 municipalities. And into this sub-network, we had 21 bridges along 3 main routes of regional interest. And we performed a life cycle assessment of the risk, evaluated as annual rate of exceedance of a certain cost level. And this analysis allowed also to identify the different role of the network against the transportation of people and goods, particularly associated with light vehicles and heavy vehicles. And as you can see, even if for this particular network, heavy vehicles are not an issue for what concerns the evaluation of the risk, after a certain time, about 50 years of lifetime, because of the higher occurrence of slight damage states that are associated to traffic restriction for heavy vehicles, you can see that the situation will abruptly change. So heavy vehicles will become the critical aspect into the system. Of course, there are several aspects that need to be further investigated, and an effort is ongoing in the civil engineering community, as you know, to promote further advances in the life cycle design of deteriorated structural systems under uncertainties in order to incorporate life cycle concept in design codes and standards, and also to take into account the potential impact of climate change. This is very important because what we need at this stage is to fill the gap between theory and practice. And effort is ongoing within several associations. Of course, we are here in the Eurostruct environment, but there are several other associations that are also working along this field. And I would like to mention the International Association for Bridge Maintenance and Safety, the International Association for Life Cycle Civil Engineering, and of course the American Society of Civil Engineers. I would like to bring your attention in particular on this technical council established within the Structural Engineering Institute of the American Society of Civil Engineers in 2008. It's a technical council on life cycle performance, safety, reliability, and risk of structural systems. And in order to accomplish its goals, this council founded 3 task groups, each one addressing a different aspect of the problem: life cycle performance for structural system under uncertainty, reliability-based performance indicator for structural systems, and more at the system level, risk assessment, structural infrastructure facilities, and risk-based decision-making. I will also mention this special collection of the Journal of Structural Engineering if you are interested in the activity of the Technical Council, risk-based life cycle performance, structural systems, state of the art. And this collection is representing the archival work of the Technical Council over the first 8 years of its existence. And after this collection was published, a couple of special projects were founded by the Structural Engineering Institute, and the results are published into these 2 books. The 2 projects were on life cycle design assessment and maintenance of structures and infrastructure system and risk-based structural evaluation methods. And in both cases, the purpose was to incorporate the concept associated with life cycle design assessment and maintenance and risk-based concept into professional practice. Recently, another project has been funded by the Structural Engineering Institute on the effect of climate change on life cycle performance, safety, reliability, risk of structural infrastructure systems. And we recently started this project with a kickoff meeting. And the motivation of this project is, as mentioned, the strong evidence that global warming and climate change will have a significant impact on long-term performance of structures and infrastructural facilities. And also current standards and codes for structural design are still based on historical data and associated loads and load combinations. Therefore, there is a strong need to promote further research to apply the scientific principles of life cycle performance, reliability, and risk to incorporate the effect of the climate change. And the goals of this special project is to review available information on these issues and identify methodology and tools that can help the civil engineering profession. We recruited 32 project members up to now that are working into this project, and we created these 3 working groups, each one addressing a different aspect of the problem: climate projection models and data, impact of climate change on infrastructure performance, and life cycle risk-based decision-making in a changing climate. Of course, there are several urgent needs that need to be addressed, not only the effect of climate change. In this survey, we noted that advanced life cycle models are now well established for some of the most detrimental damage processes, such as corrosion and fatigue, and will become rapidly available for a wide spectrum of mechanisms. However, these models are very sensitive to the change in the probabilistic parameters, and what we need is a robust validation and accurate calibration of these methods. And in order to fulfill this need, we need to gather new data, particularly from existing structure and experimental tests. In concluding my talk, I would like also to mention about this project that has been recently established in Italy. Is the Bridge 50 research project investigating the residual structural performance of a 50-year-old bridge. And this project includes a wide experimental campaign with full-scale load test on the structural members of concrete viaduct dismantled after a lifetime of about 50 years. This project includes several partners, Politecnico Milano, Politecnico Torino, and several public authorities and private companies. Here is an aerial view of the viaduct. It's a 50-year-old 80-span double-deck road viaduct. And the main bridge span were ranging from 16 to 24 meters for a total length of about 2 kilometers. And the bridge deck is formed by a system of precast pre-stressed concrete beams, including inner I-beams and 2 lateral box beams. And of course, the first stage of the project involved a series of preliminary activities conducted on site before the dismantling of the bridge. And these activities included visual inspections that were conducted according to national and international standards with the participation of several local and national public authorities and private managing bodies. The participants have been organized in inspection teams, and each group filled one or more inspection forms according to different standards established in Italy and other countries, including the United States and Canada. The data gained through this activity will be elaborated according to inspection models typically used in practice and compared with the outcomes of the experimental research. So the bridge was demolished in 2019, and as mentioned,
a small note that we should conclude soon so that we can take questions as well.
Thank you. I'm going to conclude in 1 minute. The bridge was, as mentioned, dismantled in 2019, and we a set of 29 deck beams and 2 pickups have been collected from the deconstruction of 2 adjacent spans. You can see here the cutting using diamond wires, and we also drilled the direct beam to accommodate the lifting equipment. And after the beams were lifted and moved by trucks to the testing site, the beams were also accommodated over new jerseys and stored for the experimental activities. The experimental activities to be carried out on site include photographic mapping of the structural elements, drone surveys, non-destructive diagnostic tests, and full-scale load tests, and a large number of samples for laboratory tests. Few pictures just to show the preliminary non-destructive testing for mechanical characterization of the material, the 3D modeling for the mapping of the crack patterns, comparison of what we have in situ and what we can do with this 3D modeling, And the final and most important activity will be load testing on up to collapse of the beams and using this 4-point scheme. Here is a view of the testing equipment that was designed, and this is a picture of this equipment on site with the first beam ready to be tested. At this stage, we completed the first test and we are in the process to elaborate the results of this preliminary test. And if you are interested, you can get additional information about this research project on the official website, bridge50.org. And we hope with this project to gather a large amount of data, suitable statistical processing concerning the residual structural performance of existing concrete structure and contribute in this way to knowledge advances for public authorities and improve existing criteria and methods for life cycle design, assessment, and maintenance of bridges and infrastructure networks. With this, I conclude, and I thank you for the attention, and I apologize for taking too much time.
No problem. Thank you for a very comprehensive presentation and a lot of topics covered. We will now open the floor for questions, so please feel free to write your questions in the chat, or rather send them to the Eurostruct Association contact in the chat so that we can transfer these. Maybe a first question from my side, since you showed the importance of assessment of a structure as is, and how also it is significant to know the position of critical elements like reinforcement within our system. What would you say, or how would you suggest that we combine non-destructive evaluation tools in order to update our models so that we can best assess their reliability?
Yes, this is quite a critical issue. I agree with you, because inspection procedures should be properly designed in order to get information on the most critical regions of bridges. And this is not always evident, even because this critical region may evolve in time due to deterioration. For example, when we talk about durability, generally we refer to the characteristic of the materials. We think that materials are the key factor for durability, and they are key factors, but it is not sufficient to ensure good quality of the materials, because sometimes it's much more important the role of structural detailing. And what we can find, particularly when we look at the statically indeterminate system, is that the evolution in time of aging and deterioration process may introduce stress redistribution and alter the location of the critical region. So what we consider sometimes that are the most critical details sometimes need some more in-depth evaluation, taking into account of the actual structural system that we are inspecting and for which we want to get additional information. So, as you mentioned, non-destructive testing may be an important tool for getting additional information. And in my opinion, this should be complemented with a numerical modeling that allow to well understand where the information should be considered as more relevant in order to update the life cycle prediction.
Thank you.
May I ask a question?
Please, Maria Pina.
Yes. It was very interesting, the test that you showed in the last slides on the bridge where you are testing the beams. I was wondering if you previously to cut the beams, you did some full-scale test on the entire bridge, or was I mean, the project was precisely on testing the single beams?
Thank you for this question. Because of the time, I didn't include this part, but several activities were conducted before the dismantling of the bridge, and this included the dynamic identification test. So that some dynamic tests were performed on the entire bridge span in order to compare, and additional dynamic testing will be made on site on the individual deck beams in order to compare the response on site for the entire deck and then the individual bridge, because this bridge deck typology is also characterized by significant transversal deformability, and the interaction between the beams are of crucial importance in order to capture which is the actual response of this type of system under the traffic loading. Of course, the value of the load testing on single beams will be mainly related to the identification of the detrimental effects of some localized damage, and also to calibrate the numerical models, because we already developed several nonlinear analyses that allow to follow the evolution of the experimental test up to collapse. And this, in my opinion, will be of great value, because we don't have a lot of basis for the validation of numerical models. We have a lot of experimental tests, but developed based on accelerated corrosion techniques, and not always this reproduce accurately and properly what we have on site.
Thank you. Yes, this problem of experimental data and the possibility to get some results on real structures is really important, also for dynamic tests or for damage detection tests. One of the main problems is the lack of data. So I really appreciate this type of project.
Thank you.
Maybe a more general question from the audience, from Egor. Which issue from your experience tends to govern the bridge replacement? Is it more because of a structural deficiency, or because the bridges are functionally deficient or congested?
So I believe that dismantling of the bridge is mainly associated with the redesign of the network, rather than because of serious deterioration problems. Of course, there are exceptions, and unfortunately, these exceptions are associated with dramatic events, as mentioned at the beginning of my talk. When you have a bridge failure, very frequently you need also to consider the possible dismantling of similar structures, perhaps or structures that are along the same line of the network, and this may also be something that may lead to take a decision on the dismantling. But mainly I would say functionality rather than the structural deficiency that are generally fulfilled by proper repair activities.
Yes, and maybe on that note, if I can shortly ask, in the different models you have for predicting resilience, for example, you need to probably take into account or model the effect of repair onto the system. Is this an easy action to do, or what is the proper way to produce a model for this, let's say?
Okay, so this is one of the open issues in resilience assessment. Also on this aspect, because of the time, I didn't show details, but of course, there is an important research that is ongoing on how to establish, at one end, efficient repair models, and on the other end, how to calibrate these models. Generally, these models are developed in such a way that they are sufficiently flexible to accommodate the main parameters that are associated with the repair activities. And this calibration should be also made with reference to the specific repair. I mean, the recovery curve that we were talking about is different if we need to recover from a slight damage state or from an extensive damage state. And the same recovery model perhaps need a different calibration if applied to these two different situations. There are several models that have been proposed in literature. We also proposed a model, but if I would say what we need to calibrate in resilience assessment, perhaps the recovery models are those that need deserve much more attention and research effort.
There is a question for the audience. What type of sensors are used for continuous monitoring of bridge beams? I'm not sure if it's referred to the last test or maybe to the Certosa cable bridge that you showed. the question is not specific.
Okay, so I presented two examples, one related to reinforced concrete bridge with simply supported deck beams. And in that case, we used satellite-based monitoring. So this is something that for long-term monitoring, in my opinion, may be extremely effective because they involve low-cost sensors and allow to directly process the information about displacements that may be used to analyze which is the structural response, and also allow to focus on which is the static behavior of the bridge under long-term loading rather than transient loading or traffic loading. And this is very important to monitor in time, which is the health of the system. And the other sensor that I have shown for the Certosa bridge were more traditional because we're just aimed at the measuring. So they were clinometers and load cells, the clinometers mounted on the top of the pylons and the load cells in order to evaluate mounted on the stays. So in order to evaluate the pre-stressing force. And other type of sensors that I would like to use for complementing long-term monitoring, for example, that was not installed in the bridge that I was talking before with that we monitored with the satellite-based system, are load cell to measure the weights of the traffic loading. And this is not just to have an accurate measurement of this, to have accurate data on this, but just to have a clear indicator of what may be the reason for an abrupt change, for example, in the behavior of the structure. So if you, in the long-term monitoring, find that the structure has an abrupt change in the stiffness, for example, it is important to identify also the damage. And this may be associated with aging and deterioration, or may be associated to some sudden damage, for example, because you had an exceptional vehicle that passed through the bridge. So, and information about this aspect, in my opinion, is extremely important for long-term monitoring. I'm not talking about classical weight in motion systems that are aimed at getting and gathering data for other purpose, but just as a filter of this kind of information, just to know if there is some kind of anomalies that should be associated to the effect of external loading.
Maybe one more question from our audience, from Spiros Konstantis. Are you using cameras or drones to identify defects in areas where human access is difficult or dangerous? And would you also use this to create a 3D representation of the bridges? So this is more in the direction of exploiting building or bridge information modeling, I would say, for assessment as well.
Yes, these are also important tools, and that we also use it in the project that I mentioned. For example, in the bridge where the satellite-based monitoring system was installed, we had also an hydraulic monitoring because it was a river bridge, and this hydraulic monitoring was based also on the use of cameras. That is very important in order to monitor what happened in terms of debris and so on. And the use of drones is also extremely important. In this period, we are making inspection on a series of railway bridges characterized by very tall piers. And in order to solve problem with the accessibility problem, in order to have inspection that are sufficiently close to the components, the drone surveys can really provide an extremely important support. So when you have very tall pier, for example, you cannot use also platform to get closer to the deck, and sometimes this is the case for railway bridges, it is difficult to access at the level of the bridge deck also. And in that cases, the use of drones can be extremely helpful.
There is another question from the audience. Fire Namura asks, what is the most appropriate concrete mixtures to reduce the effect of corrosion?
Okay, so this is also an important topic, how to develop new materials that are able to mitigate the effect of deterioration processes. And there are, of course, several researches that are ongoing into this field. Some of my colleagues at Politecnico are very much engaged with these topics. And you may have, for example, the use of fiber reinforced concrete that in some way may reduce the effect of deterioration, but the most promising approach, in my opinion, is the use of self-repairing concrete material that are special concretes that allow in time to mitigate the effect of corrosion, because reduce the effect of cracking, for example, and therefore will contrast the diffusion of aggressive agents. And in my opinion, this is a very promising research field. And to what I can see, I believe that also the incorporation in practice of this kind of techniques is not so far away.
Maybe a question from my side, because you mentioned this large experiment, or let's say these 9 bridges that are instrumented with monitoring systems, which are displacement measurement systems, if I understood correctly. Are you using, in what way are you using the information from these systems to update, let's say, the models of these bridges, if this is relevant? Do the displacement monitoring systems give you also dynamic information so that you can update stiffness properties? Is it primarily in terms of the deflections and so forth?
So this project with the Lombardy region is a very wide project that involved several departments at Politecnico di Milano and several colleagues with different expertises. And so we are now in the process to exploit these expertises, also to incorporate the results of monitoring into the risk assessment procedure. However, at this stage, we are just, the systems started to functioning just a few months ago, and we are still in the process to gather a sufficient amount of data to be elaborated. And we are also in the process to start the second part of this project that will be focusing specifically on this aspect, how to incorporate the information coming from structural monitoring into the risk assessment procedure. Maria Pina is also involved into this project, and yes, this is an important part that will receive a lot of attention in the next developments. But till now, we didn't afford this part of the project.
Just a comment: the monitoring system is also dynamic. It depends on the bridge. So
okay.
Yes, you are right, Maria Pina. So the 9 bridges were selected in such a way that different structural typologies have been investigated by structural monitoring, but also for each typology, a different type of monitoring system was also designed, static and dynamic, traditional or innovative, because the main purpose in this preliminary part of the project was to provide the bridge authority with guidelines on how to design and implement this kind of monitoring system, and how to support the local administrations in affording this kind of problems. And as mentioned, the next step will be more focusing on how to incorporate the data from structural monitoring into the risk assessment procedure.
There is a last question from the audience about fiber reinforced concrete. What is your opinion regarding the use of this material for durability?
I believe, yeah, this is an option and may provide some advantages in some specific applications. So when possible, this may be of course used, but I would like to stress what I already mentioned before. So when you look at durability problems and life cycle performance of systems, a key issue is not only the quality of the material or the ability of the material to prevent the evolution in time of damage, but also the structural detailing, because according to my experience, the main problems that we have in deteriorated bridges are related to structural detailing. Structural detailing that are not related to the use of the type of material used, but how the bridge has been realized and how some details are considered. For example, how the supporting devices are protected, how the system for the water distribution over the bridge is conceived. Very often problems are related to incorrect flow of waters over the structure, and this will also compromise some structural details. For example, the Gerber joints. Gerber joints are a critical issue, and this is mainly related to the design of this specific detail and how the specific detail will be protected in time. So again, when possible, let's use advanced materials and advanced techniques in order to improve the quality of the materials, but all the time we have to focus our attention on structural detailing and also aspects at the system level.
Thank you very much. We would have to conclude now, conclude our broadcast. I want to thank you very much for both the presentation and the very nice elaboration and the presentation of these projects. I also want to thank Maria Pina for co-moderating this session. And maybe as information before we close, our next LiveTalk event is next Wednesday on May 12th at 4 p.m. again, Central European Time, and it will be offered by Ernst Niederleitingen on the topic of non-destructive testing from simple detectors to deep insights, which ties a bit with what Fabio showed, especially in the end. So we look forward to welcoming you to that event as well. Thank you again.
Thank you, Eleni, for sharing, and thank you, Fabio, for the very interesting presentation.
Thank you once again for the invitation, and thank you all the attendants for sharing their time this afternoon. Thank you.
Goodbye. Have a nice day, everyone. Yes, bye.
Bye.